Ever since I was a kid, I was riddled with this question. Let's say humans traveled to Alpha Centauri star and became an interstellar species. According to physics, if we send a "How are you" message from Earth to the people on Alpha Centauri, it will take 4 years to reach them. And if they respond, "We are fine, how are you?" it will take another 4 years to reach us. How could we do real-time communication? Maybe a portal. For long I thought the answer would come from physics, but recently I realized a solution may come from neuroscience. Few years ago, I had just completed my PhD. My focus was to measure and analyze the brain activity during repeated events. We knew that brain activity decreases for repeated and predictable events, while it increases for novel and surprising events. I was using ready-made tools and functions to do regression analysis, but at some point I decided to implement multiple regression by myself all the way down to the basic math operations with no magic functions. So I came across this thread on Stack Exchange which asked how to do regression on 2 variables. The first answer was a typical textbook answer, which used matrix inversion. However, the second answer was a less known approach, but a very intuitive one by William Huber. It was about predicting residual errors. This immediately grabbed my attention because I saw an obvious link between this regression method and the predictive coding methods that neuroscientists think it underlies brain activities. Since then, I have explored and re-explored this method many times. I started to believe if we ever need to win a fight against Galactus, we have to master this method. I will explain how, but first we need to go through boring technical details. If you want to follow along, open a Python IDE, import numpy as MP, import matplotlib as PLT, define n as 50 subjects. Let's set x as a feature for our 50 subjects and set them randomly. Y is the outcome that depends on x and defined by the following linear equation. Number 3 here is the relation of y with x. X and y can represent any real-world values. For example, x may represent body mass and y may represent blood sugar levels. W represents the relation between these 2 variables. The bigger W means the stronger is the effect of x on y. To find W, you can divide y on x. In our case, we have 50 subjects. We can directly divide. Let's sum all the x's and y's and then divide their sum to find W. We can plot our model prediction and compare it with the ground truth. You can see the model prediction matches the truth and the solution is close to 3. However, if we add some random noise to the data, now we are getting incorrect results. To get better results, we use the least squares method. In this method, we multiply the denominator by x to get the square values. Therefore, we must multiply the numerator with x2. Now we have a much better prediction and the solution is close to 3 again. Let's say the noise is also another variable that we can measure. Let's call it x2 and rename the first x to x1. Now we have to do multiple regression to find the relation of y with x1 and x2. You may think that you can simply estimate the least squares for y with x1 and repeat that for y with x2. Let's modify our model to include both variables and rerun to plot the results again. Actually, the prediction is not bad. That's because x1 and x2 are independent here and not correlated. In the real world, this is not the case. Most variables are interrelated and codependent. Let's add x1 to x2 so that they become more correlated with each other. Rerun, you can see the prediction is bad and the solutions are off from the true solution. This is not acceptable because if we can measure x1 and x2, we should be able to find the perfect solution even if we have 2 subjects. Now we have 50 subjects. There is no excuse not to find a solution. So to find the true effect of x1 on y, first we need to remove the effect of x2 on x1. So use the simple least squares to calculate wx, which is the effect of x2 on x1, then use wx and x2 to predict x1. ex1 is the mismatch between the true x1 and the prediction. This mismatch represents x1 without the effect of x2, which now can be used to find its effect on y. You have to understand this concept well, because we are going to repeat it recursively for all the variables involved. Let us do that for x2 as well and rerun the regression. As you see, we found the correct solutions and the prediction plot fits the data perfectly. We can easily generalize this concept to more than two variables. In fact, this is the base for well-designed scientific experiments. When you investigate the effect of, let's say, obesity on blood sugar, you bring two groups of people differ in their body mass. However, the two groups might have other mismatching factors like height, gender, skin color, etc. These confounding factors creep their effects into the results, meaning that you are unlikely to find the true effect of obesity on blood sugar. So a good experimental design requires you to remove all the other variables during the design phase. If you couldn't do that, then you must collect more subjects and measure all the confounding factors so that you can remove out their effects during the analysis phase. This is how you do that: remove the effect of the first factor from all the other factors. Then use the prediction errors and remove the next factor from all the remaining factors. Do that again till you reach the last factor. Now the last factor represents itself without the effect of the other factors. You can now find its true relation with y. You need to repeat the same process for all the other factors. This will be very intensive computationally, but I found this simple trick which works well. Whenever you find the true effect of one variable on y, you can remove its effect from y. Now you can directly do the regression on the next factor and find its true relation with y. You can repeat that for all the other factors. The last prediction error for y should approach 0 if there is no other hidden factors and y is linearly dependent on these variables. Implementing multiple regression with this method is not hard. Let's define m as 10 factors and let's generate data for 10 factors. Let's define ws as the true relations. And now let's linearly combine all the factors to generate the outcome ys. To do multiple regression on 10 factors, we add 3 loops on the top of our previous code. The first 2 loops go through all the x's, removing the effect of xj from xi. Rename the other variables appropriately. We need to repeat this part recursively. To save space, we reassign the prediction errors directly to xj. Now, after decorrelating all the x's from each other, we can now regress them on y. Use a reverse loop, define wy list to store the true relations of each factor with y. Predict y with wy and the original x's. Oh, I forget that we should store a copy of the original x's and y's before using them. Let's also initialize wy list to 0. Finally, we use the prediction error to recursively remove the effect of each factor from y until we find all the solutions. Remove this. Let's print the solutions stored in wy and plot the prediction of our model, which is wy.product with x's. Change y here to the original y's. Correct the typo here, and this minus should be an equal sign. Rerun the code. You can see it perfectly predicts the data. The generated solutions match with the true weights too. You can simplify the code by merging these 3 lines and removing the intermediate variables. Do the same thing here. Okay, now we have a complete code to do multiple regression on any number of variables, and it's just a few lines of code. We can make our script run faster by pre-computing the square of x's in a separate list and calling it sx. Currently, this method is closed form. I mean, we have to provide all the data at once to find the solution. This is bad if we have a very large amount of data that doesn't fit into the memory, or if we need to update our model gradually as new data comes in. We can change our code to accept a stream of data and update the weights continuously. Define new variables to store the results of the intermediary computations. Now we can add an outer loop where the stream of the data comes. We feed the individual data points to our regression model. Remove every sum operation and add a plus sign instead, so that the variables are incremented continuously as the new data comes in. To avoid division by 0, add a small value to Sx. In the iterative approach, the true weights fluctuate a lot during learning, so it's better to directly estimate the predictions within the loop as follows. Change the reverse loop to an ordinary loop and change x's to x. Let's increase the number of the subjects and rerun. You can see as more subjects come, the model prediction becomes better. Now, if you have seen how neural networks learn, you would usually see that the training part is enclosed within a loop that runs for many thousand iterations. This is because neural networks use gradient-based methods in which the prediction error is shared among all the inputs, each according to their activity at that time. The error may not be shared fairly. That's why gradient-based learning requires setting a small learning rate so that the weights are gradually updated towards the maxima. On the other hand, recursive least squares method doesn't share the error directly. It first removes the effect of all the confounding factors on each other before assigning the blames. That's why it can learn quickly. Now, a sensible question is, if this method learns faster, why we are not using it in neural networks? Well, I think one of the reasons is that it's not so obvious how to make recursive least squares learn hierarchical and nonlinear relations. On the other hand, you can backpropagate the errors across many layers in the gradient-based methods, and because it learns in gradual steps, you can share the error across the layers and learn nonlinear hierarchical representations. Now, I have been trying to make recursive least squares methods to predict nonlinear data, so I don't think this is a major obstacle, but it's still subpar compared to deep networks. Another critic is that recursive methods are computationally intensive due to the inner loops required to decorrelate the inputs. But I don't think this is fair because recent neural networks, including the transformers, keep getting computationally intensive, as the self-attention matrix has the same complexity as the recursive error prediction matrix. In fact, I think one of the reasons that transformers learn fast is because the self-attention matrix may have a similar end function. More investigation is needed, and I personally think RLS methods need more attention because it may give us more insight on how our brain works. We know our brain learns more efficiently than gradient-based methods. We also know that our brain doesn't use backpropagation. The hierarchical structures in our brain have lots of backward and forward connections. RLS methods links nicely with predictive coding and Hebbian learning. Our brain learns from sequential data streams and it tries to continually learn from them. Now, if we use our RLS method to predict a sequential data where the upcoming data points depend on the previous points, then a large part of the recursive computations will become redundant. Only the diagonal part requires new computations, reducing the model complexity from quadratic to linear. This will save a lot of computation, especially for large models with large input size. Here's how it's done. Once we compute the regression for the initial variables, we can use forward connections to predict the next element in the sequence. Then we can use the backward connections to remove the effect of the new variable from the previous variables and store that in a temporary array, which later can be used to predict the next data again. Let's quickly implement that from scratch. Define a data stream such as a sine wave, but this can be any other sequential data. Define M as 10 factors. Define and initialize the forward-backward projections and their corresponding weights. Define an outer loop where the stream of the data comes and set the ground level of F and T to the upcoming input. Define another loop to iterate over all the levels. The backward activity predicts the forward activity. Likewise, the forward activity predicts the backward activity. Then we remove these predictions from the true activity and send the prediction error to the upper levels of F and T. Then we assign T to B. Now we need to estimate the weights. As we explained before, we can do that with simple least squares as follows. Before running, initialize the newly defined variables. Let's add a small value to FF and BB to prevent division by zero problems. Let's record and plot the error from the last level of F. Ideally, this should approach zero as the model learns to predict the data. Now we can do a lot of useful things. For example, we can use this model to generate the sequential data just like recurrent neural networks. To do so, copy this part and paste it below. Define the prediction as WF.product with B. Then we use the predicted data in place of Y's to continue generating new data points. Now let's plot the generated data. We don't need the update part, so remove it. As you can see, the model generated a sine wave. Please note that generating data like this is a bit tricky and it can quickly degrade if an error happens during the prediction process. Comment this part. You can also use this model as an adaptive filter to cancel the noise in the data. Let's predict the stream as the new data comes in. Let's compare the predicted data with the ground truth. You can see in the beginning the prediction doesn't match the data, but soon the model learns and it starts to predict the data correctly. Now let's add some random noise to the data and let's increase the samples. Let's compare our noisy data with the model prediction. The model cancelled the noise and correctly predicted the ground truth. Let's look at the prediction errors in all the levels. Define act as a matrix that stores all the activities in the forward prediction array. For a better visualization, plot the absolute values and flip the activities upside down so that the deeper levels moves up. You can see the upper levels have less activity because the prediction errors are less. This will be more obvious if we remove the noise and replot again. You see the first layers keep the activity of the original data. The second layer keeps the prediction errors that were not predicted by the first layer. The prediction error almost reaches zero in the later layers. Now let's surprise our model by adding an arbitrary value, let's say 1 at the middle of our sequential data. You see it mispredicts the data at the middle and the activity record suddenly bursts at the middle because the prediction error is high all the way till the last level. Now if you add 1 every 2 steps, it no longer becomes surprising and the model starts to learn and predict the data correctly again. You can see the prediction error reach 0 again at the higher levels, but the activity is still high at the third level. That's because the value we added is still surprising and unpredictable for the lower levels. Let's add another surprise at the middle of our data by setting it to -1. Again, you can see high prediction errors all the way to the top levels at the middle. Now let's make this event less surprising by repeating it every 4 steps. Again, you see top levels become dormant as this event is now learned and no longer surprising for the top levels. Finally, let's add 2 more surprising events. Again, you see high activity all the way up during these surprising events. I hope you see the point. What we observe here is similar to what we observed during measuring the brain activities for repeated versus novel events. The levels at which the prediction error reaches is useful for self-reflection, and it can measure the surprise level of the model. As we have explained in a previous video, we are conscious at the edge of uncertainty. Very predictable events can be boring and induce sleep. For efficiency, the weights at the lower levels can be fixed as they start to learn the higher frequency events. They can be put into a hash table to make the retrieval faster, where it has memorized every optimal action for every predictable input. The upper levels is where the connection weights keep updating. This is the conscious part of our mind where our attention lives to track the surprising events. All predictable events in our body are managed subconsciously. When you learn something very well, it moves to your subconscious. The path from your home to your office becomes so predictable that you no longer need to think about it during driving. You spend your thoughts on less predictable events like family issues. On the other hand, an equally long but new path is full of surprising turns and bumps. The higher resolution events keeps you attending to the road, making you feel the path was longer. My point is, as we learn to predict short-term events in our life, the prediction error will not reach the higher centers of our mind, and these events become part of our subconscious. That doesn't mean our mind becomes less busy as it starts to attend to the less predictable events. That means our perception for distance and time passage is altered as we start to predict longer term events. Okay, now coming back to our original question. If you send a message to a place that's 4 light years away just to say how are you, you don't deserve to become an interstellar species. By the time you become an interstellar species, you should already be able to predict whether people living on a distant planet are fine or not. You can do that by observing and tracking their data. Although the information you receive is lagging behind by 4 years, but your model should already be good enough to predict many long-term events spanning across many years. When you see an asteroid near the planet, your model should correctly predict whether the people of that planet will be fine or not. You don't need to waste bandwidth sending a how are you message. But let's say you see Galactus approaching the planet, your model becomes uncertain about the outcome. This is where you can send a how are you message and wait for the response. Actually, if you do that, you are a fool and don't deserve to become a multiplanetary species, because you should know Galactus will screw you next. So you have to take advantage and send a decoy message or try to deceive Galactus and buy more time. I don't know what the proper way to deceive Galactus is, but a cosmic level Earth can put a legendary fight against Galactus. The fight might span over 4 years, yet it still feels like 4 hours for these future cosmic level entities. In conclusion, to become interstellar species and have real-time communication is not limited by the vast space and the speed of light limit. It is limited by our intelligence level and our ability to predict long-term events. Our ability to predict long-term events is limited by our ability to learn from the errors. Since our current assessment methods are all upside down, our learning curve is all noisy and we are far from beating Galactus. Thanks a lot for watching.